Hello, good afternoon, everyone. So today we'll be talking about energy and transportation system models. Okay, so what is a system model? System is a set of things working together as parts of a mechanism or an interconnecting network. Most of what we've done so far is to think about how portions of the model sort of operate, and then from a tools perspective, learn about techniques that are employed in certain types of models. And so today, what we'll be doing is exploring sort of the interconnection of a lot of the topics we've already covered in this class to construct sort of larger scale models. And really today is meant to be some kind of an exhibit of existing models that are commonplace in the transportation and energy scientific community. So systems models are very broad and will cover a sort of large variety of topics, especially depending on who designed the system and what sort of modeling techniques are contained within them. Generally, you'll have approaches that have engineering designs, and so a lot of these are sort of bottom-up models that sort of construct a bunch of modules together. You can have models that are specifically meant to look at impacts of energy policy, impacts on health environments. And a lot of what we do is meant to help understand transformation pathways. And so we've talked about things like the adoption and diffusion of technologies, and you can integrate that into the system models to understand sort of broader dynamic impacts of a specific transformation. So when you construct a system model, the first thing to really think about is to understand the objective of your study. And so this is a way to sort of orient the design of the model and think about how the different parts of the system model can be put together specifically to address the objective and goals of your particular problem. And so this is maybe intuitively obvious, but oftentimes overlooked, where you kind of just dive into trying to build a model for the sake of building a model, and you should never forget that the sort of guiding principle in the design should be really catering everything to meet the objectives of your study. And then what are sort of the components needed to determine this outcome? Are you going to be using a lot of empirical data? Is it going to be modeled or simulated? What sorts of techniques are going to be employed? Are you going to be using like an optimization framework, a different sort of simulation framework? And then a topic that we've brushed on several times in this class, thinking about simplicity versus complexity, and thinking about how it's a very important principle to think about how much complexity is necessary, especially considering any uncertainties that are present in the model and in the system. So as I mentioned today, the first thing that we'll be doing is to look at a number of sector-specific system models And this is a way to expose yourself to different models that might be relevant to your research. A lot of these are publicly available and are resources that you can leverage. You can use existing frameworks, and getting a sort of basic grasp of how they work will allow you to essentially modify the models yourselves for your own needs if it pertains to your research. Uh, the other thing that we'll try and point out is to really start to connect a lot of the background and tools that we've been covering throughout the course. And lastly, giving some context on how you might even construct your own system models, whether it be for the course project or for longer term in your own research in the future. Okay, so this is a list of models that we'll sort of quickly go through. And actually, there quite a few of these are models that either have been constructed in Davis itself or are employed by researchers here at Davis as well. A number of these are designed by national labs, and we actually have briefly covered some of them. But again, the exposure to a lot of these system models it isn't meant to say, hey, like this is the sort of end all be all system model for this particular type of application. But again, is a good sort of learning process to tie everything that we've been doing together. Okay, so the first system model we'll be talking about is called the EV Toolbox. This is a model that was constructed here in UC Davis at the Plug-in Hybrid and Electric Vehicle Center. Platform is on R, and it's meant to deploy electric vehicle infrastructure in order to meet demand for EVs. Okay, and so this is a little sort of network diagram that shows essentially all the sort of different parts of the toolbox. So there are kind of two central questions. So who owns the electric vehicles, and where will they charge? And so the market share portion of the model is an econometric approach that looks at how electric vehicles are currently and historically have been adopted using demographic attributes such as housing, income, and also neighborhood effects. So this is a phenomenon that is basically like if a lot of people within one community or neighborhood own electric vehicles, then there's a higher sort of probability that neighboring communities will also have EVs, especially as time progresses. And that is a trend that actually has been fairly well observed in the academic literature. And so we employ that in order to make projections of electric vehicle adoption all the way out into the future, and having a pretty good idea at a really sort of high spatial resolution of where electric vehicles are going to end up getting adopted. So that's kind of the first half of the model. And then the second half of it is thinking about, sorry, I forgot to move forward on the slides. Yeah, so this is what I was describing with the regression component. And then there is the part of projecting the growth in terms of absolute numbers. It's based off of the vast diffusion model, which is something that we covered in our technology adoption lecture. So that's the first half of it with the EV that determines the location of EV market shares throughout California. And actually it's been applied to a couple other regions as well. And then where will they charge is based off of the travel behavior of vehicles that are projected to exist in those specific areas, as I was showing in the last slide. So we can actually determine commute routes. So this maps the origin and destination between EV owners' home and work locations. We can figure out the sort of total demand miles based off those commute routes. And then you can simulate charging patterns by bootstrapping from empirical data. And so we have existing data that tells us how the patterns in which different types of charging events occur. So if you're charging at home or you're charging at work or in public, and you can kind of figure out what the charging patterns are going to be based on placing infrastructure. And so this is a nice sort of condensed way of combining a lot of different modeling aspects right into this sort of system of models that helps to describe solutions to these two questions about where they're going to get adopted and where are they going to charge based off of the charging infrastructure that gets deployed to answer these particular questions. Okay. So moving on. The next model that we'll talk about is actually kind of a similar type of model known as EVI-Pro. This one is actually being developed to be open source. EVI currently under development, there's EVI-Pro 2, which is a larger extension and improvements of a lot of what I'm going to be describing here. And actually, UC Davis is working with NREL to help combine some aspects of the Toolbox model that I just described to better calibrate some of the mechanisms that EVI-Pro uses. So again, this is developed at NREL, one of the national labs in Colorado. Its original platform was based in MATLAB, but it's actually being ported over to Python. And that makes it more open source and accessible, especially as they plan to have a sort of public release of this model in the near future. It's also an electric vehicle infrastructure deployment model, but the way in which it decides to deploy infrastructure is a little bit different from what I was just describing in the Toolbox model. So this is a schematic, another sort of network diagram, and we're going to be looking at a lot of network diagrams to describe these system models. So you can see in sort of the orange boxes where you have your driving and charging simulations, your post-processing, and then the weighting and scaling. These are essentially kind of the actual model algorithms that are taking in a bunch of inputs and then providing some kind of output. So here you can see the simulations are determined by a function of the vehicle attributes. And so you can imagine if I am driving like a 300-mile Tesla versus like a 40-mile Chevy Volt, the way in which I drive or charge my vehicle might be very different. Infrastructure attributes, right? The way in which my charging simulation happens, if I am charging at a level 1 versus if I'm charging, at 120 kilowatts at a DC fast charging station, that's also going to change the simulation. And then travel data, obviously, if I'm driving really long distances versus short distances, that'll affect the simulation as well. And so all of these get put in, or the outputs of these provide these participation rates, load profiles, EVMT benefits, individual charging sessions. And this is essentially a way of getting a lot of the impacts of the simulation. And so they go through a whole bunch of post-processing to essentially figure out, okay, what is the required EVSE, which is just the electric vehicle charging infrastructure. So where do I need to put all these stations, and how will they get utilized based off of what we know coming out of the driving and charging simulations. And then this further gets post-processed to figure out sort of how many chargers I need. In this particular case, unlike with the Toolbox, where you explicitly sort of model the adoption through these Bass diffusion curves, in EVI-Pro, you actually specify exogenously values for the sales projections. And so you can use other models to help calibrate it. You can use existing projections. So for example, one of the common ones that is used in the default sort of EVI-Pro baseline scenarios were coming from the Annual Energy Outlook from the EIA. But we can actually even use outputs from the EV Toolbox, for example, to figure out what the sales projections might look like. The charging behavior itself is based off of an optimization framework, which is something that we didn't actually cover in this class. But essentially the way it works is that you can imagine I could deploy like 1 trillion DC fast chargers, and that would satisfy the requirement to charge all the vehicles with all the sort of constraints in this model. But in an optimization context, it's going to sort of as efficiently as possible deploy infrastructure such that you're sort of minimizing the total costs. And so the way that this model operates will be to provide an optimal solution that will deploy basically exactly the right number of chargers to meet the demand requirements from the electric vehicles. All right. Any questions so far about any of these models? Nope. Okay. Let's continue on then. The next system model that we'll be talking about is known as the market acceptance of advanced automotive technologies, also known as the MA3T model. So this is also designed by a national laboratory at Oak Ridge in Tennessee. The platform is built on Microsoft Excel, and it is a way to simulate market demand for advanced vehicle technologies. So this is a very sort of well-used model, especially in the vehicle choice community. To provide a little bit more background and context, we haven't talked about vehicle choice models very much. And if that's something that you're interested in, there is a class taught by Giovanni Tricella, who dives into application of vehicle choice models and a lot of the theory behind it. The basic concept is if you have a set of different goods, in this case, we're talking about different vehicles, so different vehicle models, how can you kind of figure out how likely it is that someone will buy one type of vehicle versus another? And you can base that on attributes of the vehicle, like what is its fuel efficiency, how much horsepower does it have, and what is the price. And so when you look at this and you look at sort of the sort of population of vehicles and how popular specific models are, you can actually do a really nice job of being able to, calibrate how important it is on average to people to have a certain fuel efficiency or a certain engine power. And then you can do that. You can use those calibrated values to figure out what happens if you kind of change the fleet, or if you introduce a new vehicle into the market. One of the big challenges, especially back in the sort of 90s and 2000s, when people were starting to think about alternative fuel vehicles, in vehicle choice models, you had this particularly large hurdle in that when I want to go and calibrate like attributes of the vehicle, I can't actually do it because there aren't any real sales of like hydrogen vehicles or electric vehicles that I can have data to calibrate to. And so that led to the development of actually this model, which is a way of getting at certain values of these advanced technologies without actually needing to calibrate to exact sales. And so I'll go into a little bit detail of how this happens. And so here is a high-level network diagram of what's happening in this model. Okay, and so you can see there's this whole sort of plethora of things that are happening here. Most of these yellow boxes are internal to the model, in which it's got some algorithms that are taking in certain values coming from your inputs that are in these white boxes here, and it's figuring out things like based off of consumer choices, what are the sales, how does that affect the stock, right? And that's going through like a stock turnover model. So let's kind of break this down. So the vehicle component attributes or vehicle and component attributes are coming from traditional engineering and data and assumptions. And so this is where you have things like prices and fuel efficiencies, and the way that they start to get at attributes that are connected to alternative fuel vehicles is to think about translating some of the things that are unique about those vehicles into a general form that could be constructed across different fuel types. So, for example, um, you can go from the size of the battery, um, which is exclusive to a battery electric vehicle, and the size of your gas tank, right, which is unique to a gas car, or the size of your hydrogen tank, which would be unique to your hydrogen car, to translate all of that into something like vehicle range. And so they do this with all of the sort of unique attributes of these vehicles in order to kind of um, harmonize the attributes for different technologies. Yeah, and so that's why you're allowed to include sort of a diverse set of technologies within this model. So energy prices, this includes prices for all of the unique fuels that are being considered. So gasoline, diesel, electricity, natural gas, and even hydrogen. And you can, as you want to do sort of future projections, you can put in exogenously projections of fuel prices. In this case, they use prices from the annual energy outlook. Again, it's a fairly sort of standardized data set that a lot of folks use as inputs into other models. The nice thing about this model is that one of the things that you can really dive into to investigate is to think about effects of external policies. And so all of these policies um, are then sort of translated into through this fact to perception translator, uh, are translated into changes into your component attributes or your vehicle attributes or your energy prices. And so if you had a policy that that affects the purchase price of the vehicle, you could put that into the model and it would decrease the purchase price of whatever subset of vehicles that you are providing that purchase subsidy to. And so a lot of these here, like the battery warranty, free parking, free HOV access, value of range anxiety, these are not that straightforward to translate into these sort of more engineering principles in the inputs. So a lot of work went into kind of figuring out how to derive values for a lot of these things. And so yeah, it's quite valuable in that they were sort of successfully able to translate these policies into these like quantitative effects on the inputs that go into the model. And so all of this goes through this consumer choice model, and then it figures out your vehicle sales, and then via attributes of like vehicle scrappage and keeping track of the stock, it uses this simple stock turnover model, which is another little tool that we've discussed to keep track of the number of vehicles within each technology across time. And then you can then use that's those stock numbers in order to determine energy use and impacts of that energy use here. From the energy consumption, you're able to look at things like emissions, both greenhouse gases and local pollutants. And so this system model is fairly comprehensive in being able to look at a whole sort of plethora of issues. You can think about policy issues. You can look at you can focus on environmental impacts. You can think of specifically about technology adoption. So it's a fairly handy tool that is quite widespread in the sort of transportation, again, the sort of choice modeling community. It's very well known. Yeah, and combines a lot of the sort of tools and techniques that we've covered in this class thus far. All right. So let's talk about okay, so we'll kind of diverge a little bit from a lot of the transportation system models or transportation and energy models, and here we'll talk about an electricity system model. So this is definitely more sort of focused in sort of the energy realm, but actually has been employed to be coupled with a lot of transportation related questions, especially as you know, those sectors start to get more and more integrated with electric vehicles. So this is a platform that was developed at UC Berkeley. Its platform is Python, and it is a planning investment model of the electricity grid. So this is known as a capacity expansion model. And so capacity expansion models in general are models which basically tell you how these models basically tell you how power plants in the future are going to be built to meet demand requirements from your sort of general population. And so as the population increases or as electricity load may change over time, if people start to use more or less electricity, if they're adopting electric vehicles, that sort of thing, then you may have to end up building new capacity. And you also have to build new capacity if power plants end up getting retired. And so this is a way of figuring out essentially how that happens. So here is the network diagram of the switch model, and you can see all of the sort of components of this model that are quite specific to aspects of the electricity grid. Probably so that the sort of first thing to think about, so if I were to sort of break this down, is to think about the actual power plants in the system, which ones exist, how are they getting used, in other words, how they're getting dispatched, how are they getting committed. So this is it's also it can include a unit commitment, which means if power plants have to turn on, it's known as a unit commitment, and there are specific operational considerations associated with this. And so if you, for example, turn on like a coal power plant, you can't turn it on all the way right away, and you can't just turn it off after it's been turned on for some period of time. And if you ever do kind of shut down a plant, it can't turn on immediately, and so that adds a lot of actual. It actually adds a lot of complexity into the model. It's a fairly difficult optimization problem to handle. Uh, Thinking about transmission of electricity across different zones, thinking about different types of energy sources and the costs associated with these energy sources. And so when you have a diverse portfolio of like solar, wind, natural gas, hydro, these have different properties, and they can they differ in the way that they operate, and so a lot of those considerations are important. And then balancing is so everything that I've talked about sort of on this right hand side. This is all about supply, right? This is how we provide the power, and then balancing is all about the demand. How much load do I have in my different zones? And then how can those be met by your reserves? And then you also have demand response details that can affect your balancing load. And then there are policies that have requirements for what can be built, what can be used, and how they can be used, and upstream impacts. And so things like carbon policies, things like RPS, renewable portfolio standards, all play an important role in sort of influencing the supply side. And then there are economics that factor into that decision making as well. And so the way that the operation happens is fundamentally sort of with two different items. So one is to think about economics over the lifetime. And so if you recall thinking about the sort of levelized cost of electricity or levelized cost of energy, you can't just put any power plant in. You need to figure out sort of how that operates, how a potential power plant may operate throughout that system. And in doing so, you get a picture of essentially how economically efficient it is, based off of the levelized cost. And so when the switch model decides to put in a new power plant, it has to essentially look at potentially all the different options that are available to it. So whether it installs like a new natural gas plant or a new solar farm, once it installs it, it has to like project out into the future to figure out how it's going to be used so that it can calculate like the levelized cost. And so these things get really complicated really fast as you scale up the model. And then, as I mentioned before, this is a particular type of optimization where it chooses the power plants in the cheapest way to meet our energy needs. There are a whole bunch of engineering physical requirements, right? So we think about how the economics play out in the decision-making process, but you also have to think about the physical engineering requirements of things like how fast a generator can ramp up, how long it takes generators to turn on and off. And so these are all important aspects of the model. Um, and then when it comes to fuel costs, again, so the forecasts of energy prices, um, I think this is like the third time that we've touched on this. EIA-AEO is the common one that's used to look at fuel prices over time. But you can make your own estimations through other sort of forecasting models if need be. Okay, so then another type of model. This is a similar type of model to switch in some regards, but a little bit different in others. So this is actually a model that I developed, and it's now been sort of deployed in quite a few different areas. So we've done projects for EPA, and it's being deployed in a couple of projects at Lawrence Berkeley National Lab, and so it's probably not as well known as Switch, but is getting a lot more sort of reception recently. The platform is based on GAN optimization with an R wrapper, and it is meant to simulate operation of power plants. So in the capacity expansion models, as I was describing in Switch, you need to have some operation knowledge of how the power plants get operated, but the level of detail has to be high enough that you can operate, you can do the operation in a simplified way that allows you to look at these long time horizons. Whereas this economic dispatch model dives a lot more deeper into higher resolution from a time scale and a spatial scale. So you can operate this over the entire country for all 87, 60 hours of a year, which is not something that you would ordinarily be able to do in a model like Switch. So I'll talk about one sort of specific application of this model, which is a project that we finished with the EPA maybe a year and a half ago. And so this is, again, sort of a larger scale combination of combining transportation sector system models with this energy electricity grid model. This essentially, and I won't go into too much detail, but similar to a lot of the ways that I've talked about it with previous models, we develop this vehicle simulation model that figures out charging profiles and electricity demands. You feed that into the grid dispatch model alongside a baseline of your electricity demand. So this is saying, okay, if I have a base load of power load for powering people's lights and their fridges and their TVs and all of that, and then I add on top of that electric vehicle load, what plants are now operating differently in order to meet that additional load, and then you can sort of isolate the effect of these plants to understand the grid implications of adding electric vehicle load. Yeah, and so for the vehicle market, the forecasts are based off of some modified versions of AEO projections. And there's actually a lot of work that was done by another sort of consulting group to help look at realistic projections of vehicle efficiencies that are actually based off of another sort of engineering model known as autonomy, which is a engineering-based drivetrain calculator that determines how a drivetrain will operate when you drive a vehicle on the road. The charging forecast, we actually covered this in one of the previous lectures, where we do bootstrapping profiles from real data in order to create these load profiles. And all of that ends up getting combined into into the dispatch model. And so likewise, there are a whole bunch of engineering constraints, the ability of power plants to ramp, an understanding of their efficiencies and heat rates, capacity factors for renewables. So you have to put in like load profile, or not load profiles, resource profiles for wind and for the sun in order to accurately figure out how much power the renewable sources can produce. Okay, and so the primary output of this is basically telling you, okay, what plants are turning on and off. And essentially that's the output of the model. But from this, we can look at a whole slew of different impacts. We can look at different energy use and fuel consumption. We can look at costs of the electricity. We can look at emissions and impacts associated with that. You can even go downstream and look at pollution, impacts on health. And so, you know, this can actually be fed into further sort of models. And actually, I'll give a higher level. So this is actually from another study that's conducted by a group at Lawrence Berkeley National Lab, where they have sort of a system of models, right? And so that whole set of diagrams you can kind of fit into here. And this, I won't go into detail on this other than to kind of point out the fact that there are a lot of sort of potential linkages in between you know, your travel or your transportation sector models and your energy sector models that get put together into these even larger scale models that can look at, you know, very sort of different questions. This particular study is looking at a sort of really futuristic scenario of what happens if you have a whole lot of autonomous, shared, and electric vehicles. And so we combined these previously developed models. So the RISE model is this one that looks at new mobility services and how they operate differently from privately owned vehicles and that sort of traveling. EVI-Pro, as I discussed before, about electric vehicle infrastructure deployments, and then the GOOD model, which is focused on the operation of the electricity grid. We can put all of these things together in order to understand how this sort of larger system works. And so that's kind of going to be the thematic elements as we move forward in today's lecture, thinking about sort of economy-wide models. And so these are kind of like the biggest, largest scale system models that currently exist. And a lot of these are meant to think about large scale problems such as climate change. Okay, and so let's take a 5-minute break right now as we, before we move into these integrated assessment models.
I have a quick question.
Yeah.
About the GOOD dispatch model.
Yes.
Did it consider the reactive power or just the active power?
Yeah, it doesn't do power flow. You would not be able to run a nationwide model that does power flow and thinking about a
Yes.
lot of those dynamics. Yeah.
Yeah, because the reactive power is essentially a unit commitments problem.
Yes, it is. And when you do reactive power, it turns, yeah, if you're familiar with, optimization, it will
Yes.
turn it into an integer problem,
Yeah.
which is much, much more difficult at these scales. So for a nationwide operation of power plants, it's, I think, what is it? The model is currently at like 20 million variables with 50 million constraints. But it is a linear system. And so you are able to, get a run done reasonably quickly. But if you turn that into a mixed integer program, uh, that would probably you probably wouldn't be able to solve it within any sort of reasonable amount of time.
Yeah, because I examined the optimal power flow beat and beat out the reactive power. And when we removed the reactive power, the voltage changed and the output of the generator has been changed also.
Yeah, so I think that when you think about like power flow, that is particularly important at uh, at a certain sort of scale to understand operation. And what you're talking about is a really valid concern, is that if you don't include, certain aspects, and all of these models simplify the systems in certain ways, there is a question of, of how accurate the operation is actually being. And so one of the important things, and I think this is an important principle for any sort of model, is if you have the ability to, you should always try and do some sort of validation. And so what we actually did with the good model was we compared against real empirical data of operation. We can do retroactive modeling of the dispatch, and we compare against a whole bunch of metrics, like how do they operate, how do individual power plants operate compared to historical data, what is the sort of aggregate level of emissions, and that sort of thing. And so we did a lot of validation testing on outputs of good, and they're definitely not going to be perfect, but for a lot of the purposes in aggregate, they end up being fairly accurate to historical data.
Yes, thanks.
Yep. I will be right back. All right. Feel like that was a quick 5 minutes. Okay. So actually, I should also mention that today's lecture is actually kind of a combination of what was supposed to be 2 lectures, and that's because we actually have another holiday. So next Monday is President's Day, so we won't actually have class on Monday. I'll still hold office hours, but no lecture. So don't be surprised if no one's there on Monday if you accidentally show up. Okay. So let's sort of move on here. So the problem of climate change is, I think, particularly salient in our in our disciplines of transportation and energy. And when we're kind of building up from this foundation of background knowledge about transportation and energy, and then tools and techniques, and thinking about these system models. And so this is kind of I would almost even say kind of like the end game for a lot of the modeling systems that we're talking about. So this is a scientific modeling effort that tries to link features of the society and economy, as well as with sort of ecological model, so of your biosphere and of your atmosphere, into a single framework. And so obviously we aren't going to cover like atmospheric modeling or ecosystem modeling in this class. And in fact, even the modeling frameworks that cover sort of society and economy, there are other portions of those models besides, transportation and energy systems that definitely stretch beyond anything that we could cover in this class. And so really what I'm hoping that you guys take away from this discussion today is thinking about how we contribute to that sort of broader framework, and how transportation and energy systems can kind of plug into that sort of larger network. So the disciplines in here span economics, climate science, energy systems, land use change, agriculture, infrastructure. So this whole list of things. And the really sort of nice thing about being involved in these sorts of efforts is that you get exposed to a whole plethora of these fields that you don't specialize in, but it's good to have some sort of baseline or general knowledge. And so the end goal of a lot of these modeling efforts is to have this uniform single framework that can assess impacts on climate change, and importantly include things like policy levers, because when we think about how we want to combat climate change, it is important to think about the large-scale systemic impacts that larger sort of policy actions can change and alter. And so these are the models that we use to essentially figure that out. So integrated assessment modeling, there are kind of 3 I think this is a fairly nice representation that generalizes components of most integrated assessment models, or IAMs. I'm just going to say that for as an abbreviation going forward. So in the green, you've got methodological aspects requiring integration. And so this is thinking about things like scenario, sensitivity, uncertainty, what sorts of methods, models, and tools that you use, and then how different disciplines kind of contribute to all of this. What are you actually kind of modeling? In this orange, you've got aspects of time and scale, and then thinking about ecological systems, and then thinking about social, human, or anthropological systems. And then there are, what are the things that we can change about the system? And so who would be involved? What sorts of issues would drive a lot of these changes? And then what sort of interventions can you apply? And so these are like policy interventions that could affect that could affect your overall system. So generally there are two types of IAMs. There's a cost-benefit integrated assessment models, and these are primarily ways of calculating social cost of carbon. Some examples of this include DICE, Page, Fund, and we'll talk a little bit about this in a moment. And then there are process-based integrated assessment models. And so these are much more complex models that dive into detail about technologies, about energy use choices, land use changes, and social impacts that are going to lead to different greenhouse gas emission outcomes. And so some of these that you may or may not have heard of, GCAM, Message, Marcal, or its newer sort of instantiation times, and the AIM model. There's just a small subset of IAM examples. Okay. Social cost of carbon. So this is something I mentioned on the last slide. So what is this? It is essentially supposed to be based on an estimate of climate change damages. So the way that you can think about this is we know that carbon dioxide and other greenhouse gases leads to climate change, right? And I can think about climate change explicitly in its impact on a whole number of factors. How it's going to affect mortality in the future, human health. If you have ocean levels rising, it's going to cause property damage. You could get into things like drought and displacement of populations, all of these impacts that climate change has. Essentially, if you took all of those damages in theory and I sort of just added them all up into some dollar value, then I could say, X amount of carbon leads to Y dollars of damage. And that would represent the if you divided your total damages, your Y dollars of total damages by your X amount of tons of carbon emitted, then that is essentially how you get at the social cost of carbon. It is the dollar per ton of carbon associated with the damages that are being caused by emitting these emitting the greenhouse gases. And so when you think about economists talking about applying like a carbon price, this is kind of the sort of baseline of what we're talking about, right? You want to, because we're not valuing these things explicitly, this is this externality, and if you capture the externality through monetizing the damages from carbon, then hopefully, that can, lead to the market essentially figuring out how to combat climate change. One of the things that's not talked about so much is that, okay, I just described that, we come up with this $Y value, but in fact, that's really sort of difficult to capture. A lot of them don't include things like some types of physical or ecological or economic impacts. And so that's always kind of this caveat with social cost of carbon, is that those Y could be a lot bigger than Y if you don't include everything, and so quantifying it can be particularly difficult. This is a really nice figure in 2007 in one of the sort of quintessential climate change reports. The IPCC basically showed these distributions of the social cost of carbon. The distributions are based off of discount rates. And so if you remember, when we talk about discounting, the damages may come many years in the future. And so depending on how you value those damages in terms of the discount rate, you can actually have fairly different values. And so at a 5%, the average is $12. At a 3%, the average is $42. And at a 2.5% discount rate, it's at $62 per ton. And this is actually a fairly older analysis now, right? This is like 13 years old. A lot of Obama era policies were based around this sort of price level. These days, the 3% discount rate is now closer to about $50 per ton, right? We are moving closer to the dates of projected damages, which is going to drive up the price because they are getting discounted less. And also as our models improve and we get a better grasp of what the damages actually are. I think this number is going to be a little bit higher when the next report comes out. It was supposed to be, I think, this year, but it's been delayed till next year because of coronavirus.
Could I ask quickly, is that $50 at 2007 level money, or is that at present day value money?
Oh,
like that an increase as it looks?
Yeah, that's a good question. I'm pretty sure it's today dollars, but there hasn't been a 25% increase in inflation since 2007. So it'll be, yeah, if I did real values instead of nominal values, that $42 will be a little bit higher, but it's not making up the total difference. Yeah, but good catch. This is a nice little diagram of the share of social costs by country. And so this is a consideration of the relative impact and contribution of the damages broken down by country. And so the size of each dot corresponds to the size of the economy. And you can see the sort of relative ratio along these lines, 1-to-1, 2-to-1, 4-to-1, of the global emissions versus the share of the social cost of carbon. And these are shaded by per capita. And so the darker sort of red it is, the higher the sort of per capita contribution is to that cost. You can see US is fairly red. Saudi Arabia is probably the reddest or the highest contribution per capita. And you can see how a bunch of these other countries sort of relate. Okay. So let's talk about how we derive some of these social costs of carbon metrics through these integrated assessment models. And so the first is looking at the first category, which is the cost benefit IAMs. This is the DICE model. And so here are a basic sort of schema for components that this model considers. So you can see that from like an engineering bottom-up modeling standpoint, a lot of the sort of technology development and adoption categories that we think very carefully about, or that we were trying to think very carefully about in a lot of our models, are kind of simplified into these sort of broader exogenous inputs. And so a lot of this stuff can be determined as inputs into the model. And so the optimization here thinks about your sort of resource categories, and it has a sort of higher resolution model of thinking about these impacts and what happens in this sort of circular structure as it's optimizing for to meet the consumption requirements that we have as a sort of worldwide population, and what that means for production, how that affects abatement, and then as you have emissions that are coming out of your consumption requirements, this leads to climate damages, and you get a sort of circular system that goes into equilibrium to kind of figure out your social cost of carbon via the sort of end state climate damages. Similarly, so this is the page model that I was describing. So it's sections at a high level your system into the climate portion, and then the economic portion. And so the climate model is, again, taking into account emissions, and then it goes through this sort of atmospheric and ecological system model that figures out what the damages are, and then these go into your economic model to figure out how these damages are affecting the economy, there is actually something specific about equity weighting, that this is not necessarily thinking about like specific communities. It's actually more about sort of country level equity and contributions, and how they're affected by damages, and how costs are allocated. And so this is another sort of model that that by figuring out what your damages are can hopefully determine with some level of accuracy the social cost of carbon associated with operating your economic model to meet the consumption needs of your population. And to give some sense of what the sort of estimated damages are from CO2 per year, this is a sort of as uniform as possible way of looking at a couple different models and looking at the estimated annual damages on a dollar per ton basis. And you can see that the sorts of impacts are fairly different among even these sort of well-developed climate models. In the DICE model, it's probably the simplest, where it allocates damages by things affected by sea level rise, and then things that are not associated with sea level rise, SLR. Compared to Fund and Page, which both have a lot of other sort of additional breakdowns of damage categories. So things having to do with cooling, agriculture, other damages. You actually even get some benefits. So I can tell you that some of the benefits that are happening here have to do with agricultural productivity that may actually increase in some areas due to climate change. So you think about as the globe warms up, you actually get a little bit more arable land in some in many areas around the world, which increases agricultural productivity. But you obviously get a lot of other sort of damages, and those benefits end up disappearing over the next century, according to a lot of models. So the range of damages is on the order of $1 to $4 per ton, and the reason why we end up getting higher social cost values is all of those damages have to be cumulative and sort of integrated to our sort of policy year where we think about implementing that tax. And so this is all sort of cumulative over time. All right. So those sorts of integrated assessment models are higher level, simplified versions of the economy in order to mainly focus on determining these social costs of carbon numbers for impacts. Process-based integrated assessment model are a lot more focused on sort of what's going on what's going on inside your anthropogenic system. So that first category, benefit costs, IMs, they're highly aggregated models. They're relatively simple and give approximate values for a lot of the factors, whereas process-based gives a lot more detailed results, but you're making a really big complexity trade-off. And so in this case, it may actually be even more difficult to incorporate things like uncertainty because you have so many inputs and so many parameters to work with. Okay, this is a really sort of generalized figure of IAMs. So you've got your and this actually kind of lines up with that previous diagram that I was showing with the green, blue, and orange. So you've got a lot of your inputs and drivers, and then you, in your blue, in the green, you have your model of how the system essentially works, and then in orange, you have your sort of outcomes and impacts. So as I mentioned before, there's a whole slew of different integrated assessment models. These are some of the sort of largest well-known models. There are hundreds of papers, written coming as outputs of these, and a lot of these models are, heavily referenced by the IPCC in developing a lot of the reports on climate change and impacts. A lot of them are derived from these types of system models. GCAM is probably one of the biggest ones. And that one is a joint research effort headed by National Lab, PNNL, Pacific Northwest National Lab, as well as a university in College Park, Maryland. Davis has done work with the message model as well as the newer developed model version of message called Times. And this was originally put together by this institute in Austria called International Institute for Applied Systems Analysis, usually just called IASA. And that is another integrated assessment model that has a lot of focus on energy and technology. So this image model, the integrated model to assess global environments, is this sort of large scale IAM, and they provide this nice little diagram that shows kind of its position among integrated assessment models in terms of complexity in understanding the environment versus economics systems. And so this model is definitely more on the spectrum of thinking about the sort of ecological and atmospheric and climate sciences part of it, where the anthropogenics modeling is probably a little bit simpler. But like most IAMs, to provide some examples here, it is tuned to be able to identify response strategies. And so, if a particular country says, hey, we are going to get this many electric vehicles on the road, or have this amount of solar or wind being installed over this period of time. These are the types of models that can take that information and then put it through this entire system and figure out, okay, that's going to, reduce, our radiative forcing to, 2.5 degrees instead of 3 degrees, and the impacts of that are going to be, X, Y, Z. The nice thing about a lot of these models is kind of pointed out in this bullet here. So how the future unfolds if there's no changes. And you can look at these baseline or business as usual scenarios, and those can serve as catalysts for change, because you can see the severity of the climate change impacts that result if we basically do nothing. And then we can see, what happens if, for example, everyone meets the Paris climate agreements. You can put in those sort of policies into these models to figure out what the impacts are. So diving a little bit more into this, so those network models that we were showing consider the complexity of this integrated assessment model, which, right, is thinking about your entire global environment. So you're thinking about climate change, land use change, biodiversity, nutrient cycles, all of these ecological stuff that we don't even touch in this class, but it also includes a lot of the stuff that we do think about in the economic system, and in technology, in emissions, in policy. And so just to give a small sense of the operation of this and things that are included, just this sort of small box up here includes all of these, production costs, trade restrictions, energy resources. So there are a lot of details that go into this that even a small section of this can rival the complexity in system modeling of the energy and transport sector models that we had discussed earlier. So here, for example, when thinking about energy supply, this energy demand, energy conversion, energy supply, these interactions kind of replicate a lot of the interactions that we were modeling in our sector-specific models, and that's all kind of just playing a small part in this larger integrated assessment model. As we kind of might end with emissions output, right, coming out of activity and our energy demand, and we kind of wrap it up there. But in this larger scale one, it thinks about circularity with the climate policy, and then with emissions going out into the climate modeling side of your integrated assessment model. And so I should mention that these types of models are built by these huge team of scientists with a huge range in different focuses and specialities, and so that the type of stuff that we talk about in this class in developing these sector-specific system models are very valuable in helping to contribute to the construction and inputs of parts of this model. It's a really big sort of team effort to put this sort of thing together. I'll talk a little bit about GCAM, the Global Change Assessment Model. So this is another integrated assessment model linking economic, energy, land use, water, and earth systems. It runs in 5-year time steps, and it evaluates a lot of these external changes that we've been mentioning before. So socioeconomic developments, climate change, treaty compliance, technology developments, energy policies. So this model is definitely on sort of the other end of the spectrum from image, where it puts a lot more emphasis into sort of the economics and social system compared to the climate system. And so there's a lot of detail that goes into specific demand factors in specific technologies in the way that markets work. And in sort of agriculture, it includes things like land use change. And so a lot of what is going into the energy system here is going to be at a level of resolution that maybe is not quite at the same sort of level of detail that you might see in like a sector specific model, but still captures quite a bit in sort of the background and driving force behind behind a lot of the developments you might see in a sector specific model. And so within this energy system, you can see specific things like demand technologies for like a specific transportation sector end use. So how many like electric heavy duty or hydrogen heavy duty ton miles you might see in a specific year. That is actually something at a resolution that you could see coming out of this type of model. And then in the energy system, just to give even a little bit more detail, like if you dive into something like the resource space and energy conversion boxes, each of these ends up actually having a lot of individual detail in your sort of fuel sources. And so this is actually much more of a type of system model that we might see in one of the sort of earlier sector models. So something like the switch model, you might see this sort of diagram where you're looking at markets of your different fuels and operation of your electric power sector. And that is something that can in some ways essentially be plugged into these larger scale models. From an impact perspective, these really large scale complex models have made, I think, a really big impact on the scientific community and even sort of the general population at large because of how important they are to the central reports from IPCC. So GCAM is one of the 4 models that are used to look at representative concentration pathways. These are RCPs, and so this is essentially when it comes down to it, a scenario analysis of impacts. And so we can see, okay, if I look at a specific RCP, what does that mean for temperature changes and associated impacts. And GCAM has been has participated in every climate, energy, economics assessment in the last 2 decades. There's another sort of set of scenarios besides RCP, known as the shared socioeconomic pathways. And so GCAM has also been employed for that. Yeah, and there are literally hundreds of publications based off of GCAM results every year, and so it is a really sort of significant modeling effort. And as you can imagine, the types of studies that are coming out of this modeling effort are not just, you know, these large scale, you know, climate change broad impact study. They go into details in specific sectors, and different scientists in different areas and specialities will leverage this type of model to look at specific specific interactions with, you know, whatever sector that they are focusing on. These are some of the different scenarios that I was talking about for the greenhouse gas concentration pathways, so the RCPs. So this is from the last assessment report, AR5, by the IPCC. And basically we can see, you know, given a particular concentration of CO2 in the atmosphere, you know, what is going to be the temperature outcome, and then downstream of this, what will be the economic and damages impacting from these scenarios. And so these are kind of like the prime scenarios that we talk about when we think about the reports from the IPCC. And those associated impacts are what we base a lot of our policy decision making on. And so these all sort of derive from a lot of the building blocks that we're trying to develop in this course to get at these way sort of downstream downstream effects of climate change. Okay, and yeah, this was you know, I should have put this earlier. So for those who don't know, the IPCC, the Intergovernmental Panel on Climate Change, is a body from the UN that's meant to provide science-based information on impacts and risks of human-induced climate change. It was established in 1988 by the World Meteorological Organization and the UN Environmental Program. It's got thousands of scientists and experts contributing, importantly, on a voluntary basis across over 120 countries. And so this is like a really serious effort, and it's also the fact that basically this is kind of a side job for a lot of scientists and experts, I think points a lot to the dedication of these scientists to understanding the importance and the impacts of climate change. The way that it's divided, it's got 3 working groups that tackle sort of different aspects of understanding climate change. So the working group 1 is scientific aspects of climate system and climate change. Working group 2 is vulnerability of socioeconomic and natural systems to climate change, consequences and adaptation options. And then probably the thing that most folks in our discipline associate with is with working group 3, which are options for limiting greenhouse gas emissions and climate change mitigation. And so when we think about in the energy and transportation sector, like new technologies that are really interesting to us, so like electric vehicles, hydrogen vehicles, renewables, all of these things are essentially there because we are thinking about climate change mitigation and ways to reduce greenhouse gas emissions. And so working group 3 mostly, and maybe a little bit into working group 2 are the types of things that we work on in the sort of transportation and energy fields. Okay, I'm actually going to skip these couple slides here. Yeah, and so I kind of want to end on this sort of thought where we're talking about these like pretty basic building blocks of the energy system, and then coming into these system models that then help influence your integrated assessment models, right? Those act as building blocks for these more complex models. And you have contributions of many different IMs going to into this large scale IPCC report that then trickle down to policymakers and hopefully end up making some kind of impact, right, through local action or through specific targeted policy. And so the sort of pathway is long and maybe a little bit convoluted, but I really do think that the type of research that folks do, even in this smaller transportation and energy space, can end up making a big difference at the end of the day. Yeah, and so hopefully that's some motivation for you guys working in this field to think about the downstream impacts of what you do. Okay, and so on that note, we'll end for the day. And just remember, there won't be class on Monday, so don't bother showing up. But if anyone needs or wants to chat during office hours about homework or on the class project, I will be there at 1 o'clock on Monday. And I should be getting feedback to everyone by the end of the week on your project proposals. So we'll end here and I'll take any questions for a couple minutes.